Good morning, kids. I hope everybody is staying safe at homes. Welcome back to our online lectures of high voltage engineering. Today's topic is measurement of peak values of a given AC or impulse signal. By the end of this video lecture, you will be able to explain the operating principle and the limitations of the different techniques that are employed to measure the peak values of a given AC or impulse signal. Moving on to the introduction, there is always a question of why to go for the peak measurements. As we all know that we have seen in our first unit that every dielectric medium experiences a breakdown based upon the incident voltage. The applied voltages may not always be ideal. You check the AC voltages, they may not be purely sinusoidal all the time, they will be containing harmonics. You take the DC voltages, they usually contain the ripple. You take the impulse voltages, they don't have a perfect peaks. We do experience always unusual peaks in the impulse voltages. So, for all these different types of voltage which you apply, there is always a need to identify the peak value of the voltage, because this may create a breakdown in the dielectric medium. So, we will be discussing about the techniques which are employed in the industry to measure the peak values of a given signal. We start with the AC signals. The most employed technique is the Chubb-Fortescue method, which was developed by Chubb and Fortescue in 1913. In this method, we will be measuring the peak values of the given AC signals. The peak reading AC voltmeters, coming to the introduction of peak reading AC voltmeters, you know that most of the power systems do work on the AC. If the given AC signal is a pure sinusoidal signal, then we can directly measure the RMS value of the signal through various techniques which we have already learned, and we can multiply it with root 2 to get the peak value of the signal. But if the signal is not purely sinusoidal, then we need to use a separate peak reading instrument, which is desirable in high voltage applications. One such meter is the series capacitance peak voltmeter. Series capacitance peak voltmeter, which is commonly employed for peak measurements in AC voltages. This is the fundamental circuit of a series capacitor peak voltmeter. It consists of three major components. One, a capacitor, standard one, denoted by C in the figure. Two diodes, D1 and D2, which will act as a rectifier, and a measuring instrument, preferably a current integrating ammeter, or any ammeter which measures the average value of the current. So, these three are the important components: a capacitor, a rectifier circuit with two diodes, and an average measuring value, an ammeter which measures the average value. Apart from that, you can use a protective device which has been shown in the figure, represented by the symbol P. These are the important components. Now, moving on to that, the circuit, as you have seen, the diodes are placed in anti-parallel. See, one allows the current in one half cycle, the other one allows the current in other half cycle. Make sure that these diodes do have a very low forward resistance and very high reverse resistance. You can prefer the silicon diodes. And ammeter you can include in either of the diode paths. If you see the working of this one, when a sinusoidal voltage is applied here, assuming that whether the sinusoidal voltage is an AC signal, when it is applied here, then this capacitor allows a current to pass through it based upon the amount of voltage which you are applying. So this current will be an AC signal, very similar to that of your applied voltage signal. And this current, this will be divided into these two parts. One diode will conduct in the positive half cycle, the other diode will conduct in the other half cycle. Now let us suppose if the current which is flowing through the capacitor is represented by some I, then D2 will conduct in the positive half cycle of the current, whereas D1 is conducting in the negative half cycle of the current. Now we will see this ammeter here. Now assuming that this ammeter is measuring the average value of the current, now we will look on to the operation of this circuit. See here, when a sinusoidal voltage is applied, the current through the capacitor is given by IC is equal to C dV by dt. Now both the diodes are working in opposite cycles. And see, this capital I is the measured current by your ammeter, which is nothing but the average value of the rectified current, which means it is average value of the current which is flowing through diode D1. Assuming that the D1 current is allowing the current in one half cycle, let us consider T1 to T2, then this is the average value of this IC. Now, if you substitute the value of IC, C dV by dt, and this T2 minus T1 is nothing but one half cycle. So that's why I have taken as T by 2, which is nothing but 1 by 2f. So this is your current. I is equal to 2fc integral of V, where V is nothing but the voltage which is being applied there. Now this means that if you are going to integrate V in that duration of your half cycle, then it will be varying between V max to V minimum. So if V minimum is considered to be 0, then V max can be given by I by 2fc. So the same is shown in the waveform here. This is the voltage applied, this is the capacitor current. So based upon this, you are going to measure the maximum value of your applied AC signal. The formula is V max is equal to I by 2fc. Now this arrangement is suitable only for positive or negative half cycles, and hence is valid only when both the half cycles are symmetrical and equal. And particularly if the voltage which you are applying is not uniform, or if it is not sinusoidal, or if it contains harmonics, then this method is not suggested. The same can be seen here. See, this is the first case where you do have a symmetrical sinusoidal, a pure sinusoidal wave. See the capacitor current here. It is also sinusoidal, so you can easily rectify it. Your capacitor can measure the average value of the current, which is in the shaded region here. This is the shaded region of the current. Now let us suppose in the second case, if the signal is not uniform, if it is containing harmonics. See here, this is the capacitive current. See, capacitive current is not uniform now. If you are going to use your ammeter for measuring the average value, see in the one half cycle it shows a different value, in the other half cycle it is showing a different current. So whenever you experience a downfall of the voltage, applied voltage, then automatically what happens? The capacitor current will be negative if you carefully observe. So, if there is more than one maxima in your applied signal, then the meter corresponds to the addition of the successive peaks. This one is observed when you are measuring. So, to overcome this particular problem of harmonics, what we can do is nothing but we can suppress the harmonics and then we can measure the things. So, to suppress the harmonics, I am employing here a resistor in between the capacitor and the rectifier circuit. So, this can reduce the harmonics to some extent. So, this is the modified circuit of your series capacitor peak voltmeter. So, I hope you have understood the working of the series capacitor peak voltmeter for the measurement of peak values of AC signals. Now, we will move on to the impulse voltages, how to measure the peak value of the impulse voltages. See, this is a very simple circuit where you will be having a diode, a capacitor and a high impedance voltmeter. You can use an ESV, which you have studied in our last classes, or you can use an electrometer or a VTVM. So, three important components: a diode, a capacitor and a high impedance meter. See, when you are having an impulse voltage, let us suppose we will be considering only one, either positive or negative impulse voltage. I am considering, let us suppose, a positive impulse voltage. When there is a positive impulse voltage applied here across the input terminals, then the diode conducts in the positive half cycle and the capacitor gets charged. The same is being measured here using your ESV. See here, diode D conducts for positive voltage only. For negative pulses, the diode has to be connected in reverse. When the voltage impulse appears across the low voltage arm of the voltage divider, the capacitor Cm is charged to the peak value, and immediately as the voltage signal, see, let us suppose if the impulse signal is increasing, then the capacitor will be charging. The moment the impulse voltage drops its magnitude, the capacitor will stop charging and thereby maintain its potential because it is not having any discharging path. Let us assume. So, this charge which is being stored in the capacitor will develop a voltage which is equal to your maximum value of your input voltage. The same is being measured with the help of your high impedance voltage. So, very simple logic, very simple circuit. And see here that you are using a diode. So, as a diode has a finite forward resistance, the voltage to which your capacitor is charged will be always less than the voltage which you are applying, even though if it is a smaller value. See here, this is the input voltage V of t, and this, when the voltage magnitude is increasing, the capacitor voltage is increasing and it reaches a maximum value. Once it starts decreasing, it maintains its voltage because it is not having any discharging path. So, that is why we are using a high impedance voltmeter. If you use a low impedance meter, then automatically the capacitor starts to discharge it through your low impedance. So, that is why there is always a need for high impedance meter across your capacitor. So, the error can be estimated if you know the diode voltage drop. See, this is the error. So, the conclusions are: peak reading voltmeters are employed for the measurement of peak values of the voltages. For symmetrical and sinusoidal AC signals, Chap-Fortescue method is employed. That is the meter is called a series capacitance peak voltmeter. For impulse voltages, a rectifier circuit with ESV is basically employed. And your assignment is, what is the principle of Chap-Fortescue method? Explain it briefly. You are supposed to start with your principle, basic circuit diagram, components, explain the working of each part. You explain me how the non-ideal waveforms cannot be giving perfect values, perfect outputs when you employ this Chap-Fortescue method, and why it fails when you do have harmonics in your signal. Thank you.